Hello everyone, my name is Chen Yubiao and I will give my oral report. Please allow me to introduce myself first. I'm currently studying for a PhD in the Massive Data Computing Research Center of Harbin Institute of Technology. My interest area is the data management on flash memory and SSDs. Now I will start my presentation. For FSSort, external sort for flash-based solid-state drives. I will give the presentation in 6 parts. First, let's start from the background. SSD is replacing the HDDs quickly because of their excellent characteristics, such as low sum power consumption, small volume, high I/O bandwidth, and shorter access latency. SSDs have gradually become the mainstream storage device not only in PC but also in the data centers. Among these good features, most of them belongs to the flash memory. If we take the SSD as a whole, with more and more hardware resources are integrated into SSDs, which makes them for richer interoperability, as shown in Figure 1. The flash packages are connected to the flash controller through data channels, and the multi-flash packages share one channel. In general, SSD contains many channels where the tasks between channels are independent. Each channel is connected to a lot of flash packages, and the flash package also works independently. Therefore, there are at least 2 levels parallelism. The first one is the channel level parallelism, and the second is the flash level parallelism. It provides a new opportunity to speed up external algorithm on SSDs. External sorting is a core operation in data management and systems. It is often a part of many common complex data operations such as union, intersect, range query, merge join, and so on. This paper consists to exploit the interparallelism to optimize it. The structure of commercial SSDs is a black box, so we can only take advantage of the interparallelism of SSDs from the top-level approach. Up to now, there are 2 principles of exploiting the interparallelism. One is using high outstanding IOs, and the other one is using large granularity IOs, because mingled read-writes will cause performance degradation. Therefore, mingled read and write must be avoided as much as possible in the use of SSDs. For current works, let's begin with the most classical external merge sort, as shown in Figure 2. External merge sort generally runs in the wrong formation phase, and the merge runs in the wrong merge phase. Only when a block is used up, a new block will be loaded from the external memory. Finally, the wrong data blocks are loaded one by one, which prevents the internal parallelism of SSDs from working. As far as I know, currently there is only one work FSSort considering to optimize the sorting using the SSD internal parallelism. Its process can be simply divided in 3 parts. Step 1, build rows. Step 2, sort rows by the list element in ascending order. Step 3, merge the rows in ascending order, batch loading the rows. When merging, it has an advantage. For the data with high order degree, it can scan and merge in one pass. On the contrary, For the data with low degree order, it needs to scan many times. At this time, the bandwidth benefits of the parallelism may be offset by the increase of scan IOs. Compared with FSSort, Montrose is the real one-pass scan sort algorithm. Its main process can be divided in 4 steps. Step 1, build rounds. Step 2, sort rounds by the list element in ascending order. It is the same as FSSort. Step 3, merge the rounds in ascending order. When the list element of input buffer is bigger than the list element of left rounds, it will dump the data out as a new round. Step 4, when load rounds merge data inside the memory at the same time, it is called merge on the fly. Step 3 is the most important part. This is have a critical mechanism for the one-pass scanning, and it is also the main source of the I/O cost because when the data is sort degree is very low, there are too many permutations between SSD and buffer, and it will bring many abundant IOs. And its advantage is that it can save a lot of I/O when it has a high order data. When the input data is a high order. Now we draw conclusion of the drawbacks of current works. External merge sort is suitable for general situation, but its parallelism is low for the data loading depending. FSSort and Montrose performs well, but it relies on the distribution of the data. This is a partial sorting. Therefore, the research objective of the article is drawn. Our objective is to propose the internal sorting algorithm which can utilize an internal parallelism of SSDs, but doesn't depend on the data distribution. Of course, it will have a stable performance. As mentioned above, the difficulty of the external merge sort is the data loading dependence in the merge phase. If we can eliminate this dependency, the SSD interparallelism can be utilized. Our solution is that we generate data intervals in the round formation phase, and the data intervals don't overlap each other, so we can load the data falling in each interval in parallel in the merge phase. What we need to do is to ensure that the data falling in each interval will not exceed the size of my memory. This is the difficulty. We have proved that our method meets the above requirements through theory. Next, let's illustrate the general process of FSSort through the graphical method. Let's begin with the round formation phase. It loads data and generates rounds, while it collects 2 equal partition points of each rounds. At last, it stores all the partition points and select the Q equation points as the data interval in the merge phase. It can ensure that the data in each interval will not exceed the memory size in the merge phase. In the round merge phase, we prepare the data intervals. Data loading can be highly outstanding so that the interparallelism can be triggered. With data loading dependency eliminated, each phase in the ROM formation phase and the ROM merge phase of FSSort can be divided in 3 stages. Stage 1, read data. Stage 2, sort. Stage 3, write back to SSD. Therefore, we can populate them with double buffers, buffer 0, buffer 1, to parallel the external memory and the main memory process, because the two processes works independently. This is the pipeline optimization of the ROM formation phase. It has a double buffer, one buffer loading data, one buffer merging in the main memory. This is the example of pipeline of ROM merge phase optimization. Finally, we evaluate the FSSort compared with FMSort and motors at Dell PowerEdge R730 platform with 3 different types of SSDs: SATA SSD, PCIe SSD, and M2 SSD. We evaluate the algorithm with unsorted and partition sorted data generating from TPC as benchmark. So our experiment contains 2 parts. The first one is unsorted data experiment. From this figure, we can see that on the totally unsorted data, FSSort performs better than FMSort and motors. A second part is a partition sorted dataset experiments. From this figure, we can see that if the data order degree is low, motors and FMSort performs well. But if the data order degree is low, FSSort performs better than the other 2. And this is the end of my presentation. Thanks.